Okay, now we're on page 26. We're going to do some Voltaic cell solutions to the questions that were assigned. So this is a slightly different version of the packet, but the question at the bottom of page 26 is what would happen to these potential values if we used tin as the standard electrode instead of hydrogen. So the idea is that hydrogen is just a little bit of an arbitrary choice in terms of how we define all these other cell potentials. They're all defined in terms of hydrogen. Hydrogen electrode is defined as having a 0 potential, and then all of the other ones are relative to that. And so if hydrogen is able to reduce the other species, then that species is placed below it, and the electrode potential is listed as a positive voltage. And if the other species, like lead, tin, nickel, iron, is a more powerful reducing agent, then the electrons flow towards the hydrogen electrode, and it's listed as a negative potential. So the negative versus positive is just with reference in which direction are the electrons flowing with the hydrogen electrode. So it's like all relative to this standard hydrogen electrode. So if we could really pick anything as a standard electrode. So what would happen if we used tin as the standard instead? Well, all the values would just shift by 0.14 volts because that's what tins is off from hydrogen. So for example, if this became the standard and this was 0 for tin, then the next one up, nickel, is only 0.12 up from nickel. So it would be from tin. So it would be negative 0.12 now, right? And the one above that would be negative 0.31 for iron, and for zinc it would be negative 0.62 volts. So this would also work. We could use tin as the standard, but it would just change all the values in this table by 0.14 volts. The one beneath it, lead, would be 0.001, and it would, 0.1 volts, and it would be positive now because it's in the other direction from lead. So the positive negative, again, it's just in which direction are the electrons flowing relative to this tin electrode. When the electrons flow to the tin electrode from the other electrode, it's defined as having a negative potential. And when the electrons flow from tin to the other electrodes, then they're defined as having positive values. So lead would flip and would now have a positive electrode potential. Hydrogen would have a positive 0.14 electrode potential because it's that far away from the tin electrode. So kind of a random question that they could ask, but the standard choice of hydrogen is somewhat arbitrary, and others could be used as well. Okay, this is on page 29, this nickel and lead half cell. So again, using the table 24, you should quickly see that nickel, the nickel half equation, is higher in the table than the lead half equation. And now that we're good at using table 24, we can immediately know that because of that, the nickel reaction is going to go this way. This is our oxidation, which means it's our anode, which means it's our negative electrode from von of von Poe. And we know this is the reduction reaction. So this is the reduction, this is the cathode, this is the positive electrode. And we know that electrons always flow in the external wire from the anode to the cathode. So if I think about my picture, I can sort of take this, I could almost take this and I could just spin it like this and it would look like a voltaic cell. Now, I won't do that because it'll make all the writing sideways. But that's essentially what we're going to do. If we stand that nickel up like this, put it in nickel solution, and we put the lead over here in the lead solution. Don't forget your salt bridge. Connect them with wires and a voltmeter. So now the reaction can take place. The electrons will move from nickel to lead. That's what those arrows indicate. This is the negative anode. This is the positive cathode. I've already got the half equations up here, so I'm not going to bother rewriting them. The ion movement is that as the nickel oxidizes, it dissolves or falls away from the electrode, whereas the lead is plating onto the lead electrode. So they're moving towards the electrode. As the negative electrons dump into the lead half cell, positive ions from the salt bridge would move into that half cell. Negative ions would move from the salt bridge into that half cell. The overall reaction, we can just add those together. I'm not going to do that right now. The cell potentials. This is a, let's see, minus 0.26 volts, and this is minus 0.13 volts. But when we flip the nickel half equation, it flips that to positive. We add them together, and we get positive 0.13 volts for the cell potential. When I plug this into negative NFE to get delta G, I'm going to use negative 2 for the 2 moles of electrons, 96,500 and 0.13. And I'm going to divide it by 1,000 to make sure it's in kilojoules, and I get negative 25 kilojoules. And this last practice question. This one, again, we're using table 24. They've kind of highlighted what they want us to make the reaction out of. So we find those half equations. The zinc half equation looks like this and has a minus 0.76 volt electrode potential. The other half equation that they've outlined is between these two different oxidation states or charges of iron, where iron 3 plus is here and the iron 2 plus is here, and this one has a plus 77 volt electrode potential. So I can already tell that the spontaneous reaction is going to be that the zinc oxidizes, is the anode, is the negative electrode. The electrons are going to flow out here, and then this will be the reduction. So I get the positive, and I get the cathode. Okay, the only thing that's sort of missing, one, we do need to balance electrons because 2 electrons, there's only 1 here, so everything in here would need to be doubled for the half and overall balanced equation. The one missing piece is that this solution doesn't have an electrode. Like a zinc half cell has a piece of zinc metal in a zinc solution, and you can see that in the half equation. There's a solid along with the solution, whereas this one is just 2 aqueous ions. So the way you get around that is you can use other materials as the electrodes. The choices typically are platinum or graphite because they both conduct electricity, but they're very inert. So they don't actually take part in the reaction, but they do act as a surface upon which the reaction can take place. So when we draw this one, you would draw PT for platinum, and in here you could put both of those iron ions. Got your salt bridge. You've got your zinc ions, and you've got your zinc electrode. I know I'm going fast. Okay, so we know the electrons are going this way. Positive, cathode, negative, anode. Okay, so the zinc ions are falling off of this, falling away. What's happening here is the iron 3 plus ions, as the half equation indicates, are being reduced. So they are traveling to the platinum electrode, gaining electrons, getting reduced, and then falling away as these iron 2 plus ions. So there's an ion moving towards, there's a reduction happening, and then there's a moving away of the Fe2 plus. So not a typical one, not the sort of traditional metal with metal ion. We can use other electrodes to act as a surface upon which the reaction can take place. The cell potential, we flipped this one to make it positive 0.76 volts. Therefore, overall, we have plus 1.53 volts. And in our delta G equation, it gives us negative 295 kilojoules.